and welcome to Badger Talk Live Quick Picks, which brings exciting happenings, resources, and talent from your UW flagship campus to the people of Wisconsin and beyond. I'm Jiayang Wu from Hangzhou, Zhejiang, China. I'm a third-year PhD student focusing on plastic recycling through thermal degradation and working in chemical engineering department. I'm pleased to introduce George Huber, Richard Anthony Professor of Chemical Engineering. Today, George will discuss new technologies for recycling plastic waste. George Willis Huber is the Richard Anthony Professor of Chemical Engineering at the University of Wisconsin-Madison. His research focus is the design of disruptive technologies for the conversion of biomass, waste plastic, and other waste resources into renewable fuels and chemicals. He has been named a highly cited researcher in the area of chemistry, an award given to the top 1 most cited chemists. He has been published over 230 papers, more than 23 patents, and received over 50,000 citations. He is the co-founder of sustainable technology companies, Nanotech and Pyron, and serves as the director of the $12.5 million Multi-University Center of Chemical Upcycling of Waste Plastics, funded by the Department of Energy. He obtained his PhD in chemical engineering from University of Wisconsin-Madison and his bachelor's and master's degrees in chemical engineering from Brigham Young University. Please welcome George Huber.
So thank you. It's a pleasure to be with everybody today. I'm going to be talking about new technologies for plastic recycling. It could be said that our society today, we live in the plastic age. Plastics are the most commonly engineered material. We use them for food packaging. We use them for construction material. We use them to package our medicine. We make clothing out of them. We use them in our automobiles. In the US, we use 37 million tons of plastic per year. That really works out to about 740 pounds of plastic per person per year. And during this plastic production, we also release greenhouse gas emissions. For every ton of plastic that's produced, about 3 tons of greenhouse gas emissions are emitted. There's a wide variety of plastics that are manufactured. One of the critical industries that uses plastics is packaging industry. This is a very critical industry for Wisconsin. About half of our packaging material is plastic packaging. That you can kind of divide plastics into 2 types of packaging material. Rigid plastics, those are like your Coca-Cola bottles, or flexible packages, which would represent 25%. Very important industry in Wisconsin. We have 43,000 people who work in the plastic packaging industry. It provides a lot of economic benefits to the state. In the flexible packaging industry, we're the 3rd highest number of people employed in flexible packaging industry of any state, with 25,000 people working in the flexible packaging industry. And this flexible packaging continues to grow because of the diversity of it, the benefits in terms of helping your food last longer, protecting your healthcare benefits. And one of the challenges with plastics is, or one of the opportunities and challenges with plastics is, there's so many different types of plastics we manufacture. Here's the different types of plastics we manufacture in the US. We have the resin identification code. Number 1 is your PET plastic, which is shown here. Number 2 is your HDPE. Even when we talk about polyethylene, there's a range of different polyethylenes that can be produced that give you a lot of versatility in terms of making a material for different applications. So this is one of the challenges, that chemically all these plastics can be very different, causing it to be more challenging to recycle them. And we really haven't done a good job with thinking about the end of life use with a plastic. This is a global Sankey diagram that shows you what happens to our plastics. Plastics really are produced from oil, natural gas. There is some work that's going on making plastics from sustainable resources like biomass, and that can be done. And for every 100 tons of plastic that we use, only about 2% of it worldwide is recycled. There's 2 in the US. There's 2 plastics we recycle. That's really your number 1 plastic, or your PET plastic. Your number 2 plastic, your HDPE. The amount of PET plastic that's recycled is about 20%. PET, if you think about soda bottles, HDPE, you think about your laundry detergent containers or your milk jugs. And those we have a recycling infrastructure for. The other types of plastics, we haven't yet developed the recycling infrastructure. There's lots of innovations going on right now to try and innovate and design, get more plastics into this closed loop recycling loop. Anywhere from 2 to 5% of plastic ends up in the ocean. Anywhere from 25 to 30% of plastics ends up in a dump. These are unmanaged landfills, and these are really in more developing countries in Africa, South America. These are open dumps where eventually the plastics will get their way into the ocean. 40% of your plastics go into a managed landfill. So this is a landfill that's going to be covered. You're going to look at the gas emissions, the water emissions to make sure none of that trash leaks out into the environment. In Wisconsin, most of our trash is landfill. Some of it is plastic is burned or for energy recovery. In the eastern U.S. and in Europe, they do incineration, energy recovery. And 14% of plastic gets put in this recycling bin. You can downcycle the plastic where you're using it for a lower value application or a different application that it was originally intended for. There's always losses when you do your recycling stream. And then ideally, you'd like to use that plastic in that closed loop application where you can use the recycled material in the same application that was intended for, that the virgin material was used for. So I'm the director for the Center for Chemical Upcycling of Waste Plastics. We're trying to design new technologies for better upcycling of plastics. This is a center that provided, our funding is provided through the U.S. Department of Energy, the Bioenergy Technology Office. We have 6 universities involved, 3 universities in the United States. We have 2 universities in Mexico and 1 university in Canada. And we have 23 companies involved in this center. We have the pure resin producers, we have the plastic converters, we have the brand owners, and they're providing us guidance about how we could implement and what our technology and what we should work on. So this is a diagram that shows the plastic supply chain. It's a very complicated supply chain. There's lots of different organizations, lots of different companies that are involved when you think about plastics. So it first starts out with extracting the natural gas or crude oil, okay? And then that gets sent to some refinery. The refinery's main purpose is to make gasoline, diesel, and jet fuel. So that gets sent to your fuels. As a byproduct, you make different chemicals, mainly your olefins, your aromatics. This gets then sent to the polymer synthesis plant. In the US, most of this is done in the Gulf Coast. You have huge factories there that cost billions of dollars that are making your pure polymers or your pure resins. These that get then shipped to your plastic converters. Here in Wisconsin, we have a big industry on plastic converters that make different packaging materials. Okay, these plastic converters, they then sell to the brand owners. They'll send the bag, the package, and there's a lot of science that goes into each of these steps that then gets to the brand owners. They'll package your material, ship it out to the retailers, the store. We then go to the store, pick it up, okay, use the material, put it in the trash or recycling. The waste management companies then come and pick up your trash recycling. If it's in the trash, it'll go directly to landfill. If you put it in the recycling bin, it'll go to what's called a MRF, or material recovery facility. Every municipality usually has a MRF. The MRF, their job is to sort out anything that's non-recyclable, bale anything that's recyclable, and then send it to the recyclers. Okay, the recyclers will take that, they'll purify it, make resins again that don't have quite as good properties as the virgin resins, but then send that back to the plastic converters. In the state of Wisconsin, we have one post-consumer plastic recycler that's recycling plastics and making recycled PET. So with a cup, we're trying to design technologies that these recyclers could use to get more plastics back to the plastic converters. We're also designing technologies that would allow us to get more plastic into the petroleum refiners, and then they could use to remake the virgin plastics. This is the material recovery facility, or the MRF. It's a system of conveyor belts that has different sorters. They use magnets to pull out the metals. They use a range of different techniques to pull out different plastics, very sophisticated, kind of highly optimized system. And this is the product that I'm showing right here. This is the baled plastic materials that they make. One of these could be a number 1 plastic, another one could be a number 2 plastic. this is not recycled material, but this is a super important step in the recycling of the plastic. So they'll sell these bales to secondary recyclers who will take them, make different materials. This is a schematic I put together of a PET recycler. So they'll purchase bales of number one plastic. They'll then have a section of conveyor belts, remove anything out. They're very concerned about the purity here. Then they'll fragment it, grind it down to different flakes. They'll do what's called the sink float test. The polyolefins will float. The polyolefins usually are your bottle caps. Nowadays, you're supposed to recycle your rigid cap, your plastic bottles with the cap on, because they can use the sink float test to separate out the polyethylene from the PET. PET is the number one plastics, the PET sinks. They then have to clean it up really well. They'll do hot washing, add detergents, clean it up. Then those flakes will get sent back to a melting extruder. You'll make your pellets or your polyester fiber that can then be used to make the materials that we use to make plastics. We make new soda bottles, new thermoform materials, other materials. There's some degradation that can happen in here, but this is what's called mechanical recycling of plastics. In the state of Wisconsin, we have one post-consumer mechanical recycler of PET, no mechanical recycler of HDPE. There's lots of innovations going on to improve that, but there's lots of materials you can't mechanically recycle. One of them is films. Okay, so this is a mechanical recycled shrink wrap film where they made pellets from. If you look at this color, it's dark, dirty brown. It's a very low quality polymer that has very limited application. The hardest application to get your recycled plastic to is food grade applications. But there's other lower qualities that you could use this for, maybe some construction materials, maybe asphalt, things like that, you could use this other material for. So we're trying to design technology that gets us a higher quality material. So this is one person who's very famous in Wisconsin in the packaging industry named Howard Curler. He was a graduate from the UW-Madison Chemical Engineering Department in 1948. We have a chair, a distinguished chair named after the Howard Curler Chair in 1997. And he came up with this new way to package cheese. Okay, before that, cheese was you had paper, you had foil, you had cellophane, tin to package materials, and this new material came out called saran. So he had a patent to combine saran with other polymers, cellophane, polyethylene, to put them together and package cheese. Kraft used this for a long time to package cheese. And they provided a lot of the packaging for Kraft to package the cheese. But the challenge is this material combines several different plastics together to make a multi-layer plastic material. The saran is an oxygen barrier. It helps prevent oxygen from getting in there. The other materials provide mechanical rigidity. And so it's a lot better plastic packaging material, but it's more challenging to recycle because it has all of these different components on it. So we've developed a technology we call STRAP, or solvent targeted recovery precipitation. We use solvents to selectively solubilize one plastic. We precipitate it out, and we get back the virgin plastic. So here's one previously unrecyclable multi-layer plastic material we produced in the laboratory. We get white polyethylene, white EVOH. EVOH is the barrier layer they use now, rather than saran PET that gives you mechanical rigidity. See, it's white, very clear, and almost 100% yield. We could use different solvents to be able to recycle this. We do this in the laboratory. The people said, okay, that's nice you can do that in a laboratory. Let's see if you can actually make a film from that. So we start with the shredded post-industrial printed film. Here's the rolls of film before they're produced. There's a lot of waste in this manufacturing multi-layer film. We can make pure white polyethylene. We can then extrude that, make that into pellets. So here's the pure resin polyethylene, and then we can go back to a film. Okay, so this shows a way you can continuously recycle this previously unrecyclable material with STRAP technology. So it took us about 4 months to make enough pellets to make this film. So we've designed a new system to produce 25 kilograms an hour of recycled material. And this is a more industrial system that we've designed with a team of mechanical engineers at Michigan Tech University. We spent several years designing this system, building this. This is a pilot system before a commercial system. But you add the plastic in here, a solvent dissolves it, and then you can make pure resins. In the future, we hope to build a commercial system with this technology. We've identified a location in Green Bay, Wisconsin. We'd like to build a commercial plant and move these technologies forward. There's lots of options for using waste plastics. We're doing the basic research here at University of Wisconsin, and we're working with our industrial partners to try and move them forward. And we'd like the state of Wisconsin to be a leader in plastic recycling. So thanks for tuning in. Please feel free to follow us on our webpage. Feel free to post any questions in the Badger Talks Facebook group, where I'll be happy to answer. Have a great rest of your day.
Thank you for watching this Badger Talks live event produced by the University of Wisconsin-Madison through UW Connect's outreach and the Office of State Relations. Follow us on Facebook and YouTube to see the library of past recorded talks. Please visit badgertalks.wisc.edu to see the schedule of upcoming talks, sign up for the Badger Talks email list, and search the roster of over 400 UW experts who are available to give talks on important issues in your Wisconsin community.